Hello everybody, so this is the solution video to worksheet 1.4 where we were talking about function notation. And to start with number 1, we're given a function f and asked to simplify the following, basically interpret the notation into what we're supposed to do. So our function for part A is 2x plus 1, nice simple linear function. So when we're given this for part I, we're asked to simplify f of 3. So all this means is that in our original function we had a variable x, and this variable pops up throughout the function. So what we're going to do is now in place of that x we're given a specific input, in this case 3, and we're going to replace any x variable with that new input. So in the case of f of 3, all we would do is we would say 2 times, we replace the x with the specified input of 3 plus 1, and now we just have to simplify the mathematics. So we've got 6 plus 1, and our final solution would be 7. Excuse me. So that would be the solution to that one. And basically they're all that simple. Sometimes the input gets a little bit tricky, but they're all pretty much the same approach. So for 4x, we're going to take our function, and in place of x, we will replace it with 4x. Now, in the process of simplifying, which is sometimes the trickiest part of these, is we're going to want to distribute the 2 to the 4x. And in doing so, we're going to end up with 8x plus 1. And that's really as far as we can take it. We've got any x terms combined, we have any constants combined, and there we go. So for I, our input now is negative x, so we just replace the x with a minus x, and then distribute the 2. We have minus 2x plus 1. And that would be our solution for that one. Again, nothing more we can do to simplify. For part 4 of A, we're going to replace that x with x minus 4. And now we've got to distribute that 2 again. So we distribute the 2 to the x, and then we distribute the 2 to the negative 4. And then we've got the plus 1 still kind of hanging on there. So at this point, we do have some terms that we can combine. So to finalize the simplification, we've got 2x, and that would be 2x minus 7. And then for part 5, we've got, this one is a little bit different. So it's starting with our function f of x, and we're told that f of x is just the 2x plus 1. And now we're subtracting 4 from the function, so there's no real change to the input. So what we would do is we'd start with f of x, which is exactly what it's telling us. And f of x in this case is 2x plus 1. And from that, we are just going to subtract 4. So now again we've got some common terms that we can combine, and we've got 2x minus 3 as our final answer for this one. Okay, so not too bad. Now in part B, the function gets a little bit more complicated, not too bad, but now we've got a quadratic rather than a nice excuse me, a nice linear function, but the process is the same. We're going to take our function and we're going to replace the x with whatever the given input is. In this first case, it's negative 1. So we're going to have minus 1 squared minus 3 times minus 1 plus 2. Negatives are a great place to make mistakes in problems like this, so just make sure you're careful as you clean this up. So we're going to get a nice number here. We'll go ahead and we'll square the negative 1 to give us positive 1. Negative 3 times negative 1 is going to give us a positive 3, and then plus 2. So our final answer here is going to be 6. So with an input of negative 1, the output of this function is going to be positive 6. Now our input is 4x, so we're going to put in the 4x. We're going to square that, minus 3. And don't forget to put this anywhere that you see an x, because there's also an x with the 3. So that's going to be 4x plus 2. Now, just a little, it might seem silly, but a little reminder, this is a great place to make mistakes. This 4x squared, this is 4x times 4x. That's what's really going on here. So when you see that exponent, so when we multiply 4x times itself, we want to make sure that we're careful with our answer here. In this case, 4x times 4x is going to give us 16x squared. We distribute the minus 3 to give us minus 12x plus 2. So we've still got a quadratic function here when we do our evaluation. All right, so this last one, f of x plus h, this term pops up a lot in pre-calculus. Later on you'll see it, and again in calculus this becomes something that we always are going to be we're going to see popping up in differential calculus. So let's go ahead and just kind of get some practice dealing with something like this, because otherwise it seems a little bit abstract. So we're going to take our function, we're going to go ahead and replace the x with this x plus h term. So this is going to give us x plus h squared minus 3 times x plus h plus 2. And again, just make a note here that what we were being asked to do here is take x plus h times x plus h. The answer to this is not x squared plus h squared. We actually have to multiply these terms out. In doing so, if you want to think of it as foiling, that's fine, but what we're doing is we're multiplying the x's to get an x squared, multiplying the x times h to get a plus xh, h times the x plus xh, h times the h plus h squared. So that's what we get when we square x plus h. So we'll go ahead and we'll kind of get a collection of that up here. We've got x squared. These two terms will combine to just be 2xh, and then we've got plus h squared. Now we're going to go ahead and distribute that negative 3. So we've got minus 3x minus 3 times h, and then plus 2. So this is actually our solution here. And again, it's a mess, but for those of you who have seen this before, this is an integral part of differential calculus, making these calculations, and if you got that pun, you're probably in the wrong class. Okay, so let's move on to the second one on this worksheet. So here, the function that we're being asked to use is a piecewise defined function. And what we want to be careful of with piecewise defined function is paying close attention to these three, in this case, subdomains, because depending on what we're asked to plug into our function, we need to see which one of these subdomains that value is going to fall into to determine which piece to use. It's kind of like a function with a multiple personality disorder, and we want to make sure we pick the right one for any given input. So let's go ahead and try the first one. So to evaluate f of minus 4, first thing we need to figure out is, well, where does that minus 4 fall? Well, if we look closely up here, it's in this piece right here. Since negative 4 is a number less than negative 3, this is going to be the part of the function we're going to use to evaluate. So in place of the x here, we're going to go ahead and replace that with the value that we're asked to input, which in this case negative 4. So we'd have negative 4 plus 5, which will just give us a value of 1. And that's all you got to do. We don't have 3 answers, we just have the 1, and then we move on. Okay, so let's go ahead and try the next one. So f of negative 3. So which one of these 3 pieces does negative 3 fall into? Well, here in this one that we had just used, this is accounting for all x values that are less than or equal to negative 3. So again, we're going to use this first one, x plus 5, as the piece to evaluate the function at negative 3. So this is going to be equal to, and we just plug in negative 3 for x plus 5, and we'll get a value of 2. And that's it. Okay, so moving on to the next one, we're asked to evaluate f of positive 3. So let's head up to our piecewise defined function and see where positive 3 falls. Looks like in this second piece, this is accounting for all x values strictly greater than negative 3, but less than or equal to positive 3. So because of that less than or equal to positive 3, this is the piece that we're going to go with for part C. So we're going to go ahead and we're going to take the square root of 9 minus, and we're going to plug in our x value, which in this case is 3, squared. And that is going to give us the square root of 9 minus 9, which will just be the square root of 0. And we can definitely take the square root of 0. It's just equal to 0. Okay, so we got that one out of the way. The next one that we're asked to work with is f of 3.00001. This is just sort of here to sort of highlight the fact that we're looking at a number greater than 3. Very close to 3, but still greater than 3. So we're going to need to go to this last piece, the minus x plus 5. So we're going to have minus our x value, which in this case is 3.001, and then plus 5, right? Let's double check that. Yeah, minus x plus 5. And when we combine these two numbers, we're going to get 1.999. And that would be our answer for this one. For part E, we're asked to evaluate f of 2. So let's go back up and see where 2 falls in here. We'll get that out of the way. So 2 is a number less than 3, but still greater than negative 3. So we're going to go ahead and we're going to go back to using this one. So the square root of 9 minus x squared. So this will be equal to the square root of 9 minus our x value, in this case is 2, squared, gives us the square root of 9 minus 4, which gives us the square root of 5. And we're going to go ahead and leave it like this. Unless you're asked to round, normally we want to keep answers exact, and with square roots, if it doesn't simplify, just go ahead and leave it as a radical unless you're instructed otherwise. Okay, so let's move on to number 3. Okay, so here we're being asked to find the implied domain of the function. Implied being because of the nature of the equation that we're given in terms of this function. So finding the domain of a function is something that's going to keep popping up over and over again in pre-calculus, calculus, and beyond. You know, we're still kind of starting out in terms of which functions we're exploring. They're mostly algebraic right now. But as you go through different types of functions, you'll notice that certain ones have restrictions on the domain that we notice in general. So for right now, a couple of restrictions that I think we should make note of in terms of domain. So for now, kind of keep in mind these two restrictions. So first off, we can't divide by 0. So you can't divide by 0. I think everybody sort of knows that. It would cause it to be undefined. So when we're picking our x values for our domain, we want to make sure we pick ones that don't lead to a situation where we may divide by 0. The other one that we want to watch out for now is that we can't take an even root of a negative number. So we can't take an even root of a negative number. And that is for real valued functions. So we can't do that in terms of the real number systems. When we move into complex numbers and talk about imaginary numbers, then we can worry about that. But for now, we can't take the even root, so square root, fourth root, sixth root, eighth root of a negative number. So these are the two things that we're going to want to watch out for specifically in these examples. So let's go ahead and start off with part A. So we've got f of x is equal to x squared plus 4. So yeah, we could think about, well, what are all the numbers that I can use for x? Because that's really what we're talking about with domain, is what x values can this function use? Oftentimes it's a little bit easier for us to think about, well, what can't I use, and then get the domain from that. In this particular case, we've got a quadratic. There really aren't any restrictions that we can that we can see in this. We can plug any x value that we wanted to. Any negative number, any positive number, 0, all those work out fine. So in this particular case, there are no restrictions on x. And because of that, the domain is going to be all real numbers. We could write that a couple different ways. If you're asked for interval notation, this would be all x values from negative infinity to positive infinity. Another way that you may see this written is that x is an element, that's what that symbol means, of the real number system. And we use this double-barred R to represent the real number system. Okay, so that takes care of A. For part B, our function is the cube root of x minus 5. Now again, this is an odd root, and in the real number system, we can take an odd root of a negative number, so it really doesn't matter what we put in here. It could be positive, it could be negative, it could be 0. Taking the cube root of it is not going to be an issue. So again, we see that there are no restrictions. No restrictions, because this is odd on x. And again, we see that our domain is just going to be the entire real number line from negative infinity to positive infinity. Okay, so now we get to a problem like C, where we've got x's in the denominator. Anytime you have a function, rational function, or something that has a denominator in it where x's are part of that denominator, you're leaving yourself open for the possibility that there may be an x value that makes that denominator 0 and would need to be identified as a restriction on your domain. So what I like to do in this case is I recognize that fact, and I say, you know what? This term, x squared plus x minus 2, that can never be 0, because I never want to divide that function, or I never want that function to be dividing by a value of 0. And then what I've got is sort of like a non-equality that I can then solve for x, and those will help me identify the x values that I don't want to use. This is a quadratic. Go ahead and solve this for x. You could use the quadratic formula, or you could see if it factors. In this case, this factors pretty nicely. So we could say that x plus 2 times x minus 1 can't be equal to 0. And if we break this up, we know that, well, this means that x plus 2 can't be equal to 0, x minus 1 can't be equal to 0, because if it was, then we'd have a 0 in the denominator. And then we just sort of solve each of these. So x can't be negative 2, and x can't be positive 1. And notice that if we had picked any of, either negative 2 or positive 1 for x, plug them back in to this original function in the denominator, we would end up dividing by 0. So these are the restrictions. We can use anything else except for those two numbers. So how do we express that domain? When the domain starts to get a little bit complicated, sometimes I like to draw a real number line to get the intervals. So we've got from negative infinity to positive infinity. I'm going to plop down our two numbers of interest, and we can basically take any number on this line except for those two. So that's why I'm kind of blocking them out with holes. But anything else we can use in our function. So we can set up the intervals as, well, this is going to be from minus infinity to negative 2. We union that with negative 2 to positive 1, that second interval, and then that is then joined with the interval from 1 to infinity. And this ends up being our domain. So we can pick any number from that interval, and that will work on our function. We don't have to worry about dividing by 0. Okay, and then for D, we see the other restriction that we have to watch out for is this is a square root. We can't take the square root of a negative number. So again, we sort of set off a little side restriction here, and we say, well, I know that this term under the square root, 2x plus 5, it can't be negative. So it has to be some number greater than or equal to 0. Otherwise, I'm going to get an undefined value. And we can just solve this for x, this little inequality. So I'm going to subtract 5 from both sides, and we'll get 2x is greater than or equal to -5. Divide both sides by 2, and we get x has to be greater than or equal to -5/2. So as long as we pick x values greater than or equal to -5/2, plug them into our function, we don't have anything to worry about. This is a perfectly fine way to express the domain, but if we did need to go to interval notation, again, we could consider a real number line, plop down this number, and what we're interested in is x values greater than or equal to -5/2. So that little interval right there, and that would be bracket -5/2 all the way off to positive infinity. And then this would be our domain. So the last problem on this worksheet is actually an application, and we are told that the population of Sasquatch, and just as a side note, the authors really enjoy talking about Sasquatch, so you'll probably see this pop up in a lot of the applications in homework and in these worksheets. But the population of Sasquatch in Portage County can be modeled by this function p of t is equal to 150t divided by t plus 15, where t represents the number of years since 1803, and then we're asked to find and interpret a few values here. Okay, so the thing to keep in mind here is this function, what it's going to spit out for us is a population value. And then what we're putting into it, t, represents, as it says, number of years since 1803. So for the first one, we're asked to find and interpret p of 0. Well, we know that this notation is telling us to take the function, and in place of t, we're going to go ahead and place a 0. So this is going to be 150 times 0 divided by 0 plus 15. We end up getting a 0 in the top, we get a 15 in the bottom, and we just get a value of 0. So that's easy enough, but what does this mean? Well, this is telling us that if we have a t of 0, this sort of implies to us that the 0 years have passed since 1803. So the year is going to be equal to 1803, and then normally we'd add whatever t was, but in this case it's 0, so the year is 1803. And since the output of this function is 0, this is telling us that the population is 0 in this particular year. So we could conclude that in the year 1803, the population of Sasquatch was 0. There were no Sasquatch in Portage County at this point in time. Okay, so now let's move on to the second one. So they asked us to find and interpret p of 205. So again, the imperative here is the same. We're going to go ahead and we're going to plug in 205 anywhere that there's a t in this function. So we have 150 times 205, and then we've got 205 plus 15. All right, so if we multiply these two numbers out, we should get 3,075 divided by 220. And if we estimate this, it's approximately 139.77-ish. So what does this mean? Well, the t in this case was 205, and we know that this is related to the year. In this particular case, the year will be, since this is the number of years since 1803, we would calculate the year as 1803 plus the 205 years that have elapsed since, which gives us a year of 2008. So what we can conclude is that in the year 2008, the population of Sasquatch was somewhere, we can't talk about 3/4 of a Sasquatch, just doesn't work that way, but we could say that the population of Sasquatch was between 139 and maybe 140. We don't want to round up, we don't want to round down, but this is probably the cleanest way of interpreting this one. So that does it for this worksheet, and I'll see you guys in the next video.